The Golden State is not just known for its golden beaches, but also for its fault lines, especially the San Andreas Fault, which runs almost the entire length of the state. In January, the U.S. Geological Survey reported a magnitude 6.1 earthquake in the southern part of the fault. It was felt all the way in Las Vegas, but the real danger comes from what we can't see. While most faults are visible on the surface, the San Andreas Fault is hidden beneath the ground, concealed by over 120 miles or 200 kilometers of sedimentary rock. And it's one of the most dangerous faults in the world because we can't fully understand how it works when it's buried underground. That is, until now. A new study has uncovered some of the mysteries of this fault line that could help scientists better predict when and where it might strike next. To find out what's going on beneath the surface, researchers turned to something unexpected: a nuclear test site. In Nevada 43 years ago, the United States government detonated a nuclear bomb 922 feet or 281 meters below the ground at the Nevada test site, now known as the National Security Site. This was during the Cold War to study the effects of nuclear bombs on underground faults as part of the Plowshare program. Scientists knew that nuclear bombs could cause earthquakes, but they didn't know much about the mechanics behind it. So the U.S. government carried out 8 nuclear tests between 1968 and 1973 to learn more. These were low-powered bombs equivalent to around 10 to 30 tons of TNT. They weren't the kind that would destroy cities like the ones dropped on Hiroshima and Nagasaki during World War II, but they were enough to give scientists some answers. One of these tests, Pascal A in 1969, provided clues about the San Andreas Fault. The bomb was set off in an area known as the Black Rock Desert. Scientists recorded an earthquake with a magnitude of 5.7. But what's really interesting is that they noticed there was a delay between the explosion and the earthquake. There was a 5-second lag between the two events, and this led them to conclude that the bomb had created a cavity in the rock. The rock collapsed after 5 seconds, triggering the earthquake. In 1973, they carried out another nuclear test called Pascal B. This time the bomb was detonated beneath a different fault line called the Dixie Lake Fault. And once again, they observed a delay between the explosion and the earthquake. This time the lag was only 0.5 seconds. So scientists realized that the amount of time between the nuclear blast and the earthquake could tell them a lot about the type of fault that they were dealing with. But it wasn't until now that scientists have analyzed the data collected from those tests to learn more about the San Andreas Fault. Their paper published in the journal Nature says that the nuclear blasts caused the rock to break along the fault in a way similar to how a whip cracks. A whip snaps very quickly, but the tip of the whip continues to move forward even after the rest of it has stopped. This is due to the inertia of the tip. It takes time for the tip to catch up with the rest of the whip. And similarly, the nuclear explosions triggered the rock above the fault to move first, but the movement continued along the fault in a domino effect. But the time it took for that domino effect to happen varied depending on how deep the fault was. The further down the fault went, the longer it took for the dominoes to fall. To reach their conclusion, researchers used computer models to simulate the nuclear tests in various geological settings. They considered different depths of buried faults and different distances between the explosion and the fault. And what they found was that the depth of the fault had a significant impact on the size of the earthquake. When the fault was closer to the surface, the earthquakes generated by the nuclear explosions were larger. But when the fault was deeper, the earthquakes were smaller. What's more, the larger the angle between the direction of the force of the explosion and the orientation of the fault, the bigger the resulting earthquake. It makes sense that a fault closer to the surface would cause a bigger earthquake because there's less rock above it to dampen the energy released by the explosion. But it's counterintuitive that a larger angle between the explosion and the fault would also cause a larger earthquake. You'd think that aiming the explosion at the fault would generate the biggest earthquake. But that's not the case. This is likely because of the surrounding rock. When the angle between the explosion and the fault is smaller, the energy from the explosion spreads more evenly through the surrounding rock. But when the angle is larger, the explosion blasts mostly in one direction, causing a more concentrated release of energy along the fault. These findings have important implications for understanding the San Andreas Fault, which poses a serious threat to the millions of people who live nearby. It's been described as one of the most dangerous faults in the world because of the huge number of people and infrastructure that it runs through. Los Angeles alone has a population of nearly 20 million people. An earthquake here could be catastrophic. According to the USGS, the probability of a magnitude 7.5 or higher earthquake along the southern San Andreas Fault within the next 30 years is about 7%. For the northern San Andreas Fault, the probability of a magnitude 7.5 or higher earthquake in the next 30 years is estimated to be 25 to 40%. But the problem is that, unlike many other faults, the San Andreas Fault isn't visible on the surface. It's covered by sedimentary rocks and soil, making it difficult to study. But recent research has helped scientists get a clearer picture of what's going on beneath the surface. In 2020, for example, researchers developed a new method for mapping the fault line using seismic data. They found that the San Andreas Fault dips much more steeply than previously thought. The findings suggest that the fault could be weaker and pose a greater risk of a large earthquake. Another study, carried out in 2022, revealed that the San Andreas Fault is made up of several smaller faults that could be moving independently of each other. This could increase the likelihood of a big earthquake, because if the smaller faults start moving in different directions, they could get stuck and eventually snap. Despite these studies, there's still a lot that scientists don't know about the San Andreas Fault. One of the biggest challenges is that it's so long. It stretches for over 800 miles or 1,300 kilometers along California. And the fault isn't uniform. It has different characteristics at different locations. Another challenge is that the fault is locked in some places and creeping in others. Locked sections of the fault are more likely to produce large earthquakes because the stress builds up, until the rocks break and suddenly slip. Creeping sections, on the other hand, release their energy gradually through small slips. The southern part of the fault is mostly creeping, while the central and northern parts are mostly locked. But there's still a lot to learn about why the fault behaves differently in different places, and what controls the size and frequency of earthquakes along the fault. This is where the nuclear test data can help. By better understanding the San Andreas Fault, scientists will be able to improve their predictions about when and where the next earthquake will occur. The nuclear tests may seem like an odd source of data for studying earthquakes, but they provide a unique opportunity to learn more about what's happening beneath the surface. While no one can predict exactly when an earthquake will occur, better understanding of the fault could help scientists refine their forecasts and give people in California the information they need to prepare for the next big one. Thanks for watching this episode. We've made thousands of educational videos over the years, and we've been able to offer them for free because of our patrons. So to all of our patrons, thank you for what you do to make this happen. If you're not a patron but you want to learn more about what that means, you can go to our support page